So today I want to drive you through polynomial optimization. Like you just have to consider the following very general family of optimization problem. Sub of x1 going to xn, of fx1 going to xn, where n being our variables, such that we have gi of x1 going to xn is equal to 0, with I moving into 1m, which represents the constraints of inequality. We have also the constraints of equality, ag of x1 to xn equal to 0, such that g believes into 1 to r, with r the constraints of equality. If you see, it's less or more the same as Lagrangian, like at the primal, when you define dual Lagrangian, like the primal of a stuff, normally like sub of x of trace of cx, such that trace of fix is inferior to ai, trace of gx is inferior to bj, and so you have less or more the same constraints of equality, inequality, and the objective function. So that's it, and basically so we search to like minimize or maximize this function, under those constraints. It can be like, for example, 3x1 squared plus 2x1 x2 minus 5. Even if it seems really simple, those problems are really hard in reality. They are NP hard to resolve exactly, because once the degree of the polynomial increase, or the variable are not convex, it's hard, NP hard. And so I wanted to drive you through an example, which is the max cut problem, which is a big classical of graph theory. If you imagine like a graph with some connected stuff, the goal will be to separate the stuff into the segments in the ways, or those points of the figure into the two different groups. So there is no. So yeah, let me do it for you. Like, so imagine you have this v1, v2, v3, v4, v5. And so you have your stuff like this, and so you just draw all the lines that connect them. So there is this line, 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 and so you want like to know about if the left ones, if you're into the left ones or the right ones. So basically, let's see, we just write the left one as this, the right one, so that's the black one at the left and the white balls at the right. And so yeah, basically what you want to do is like you want like to see which one are connected or not. Like you should like draw, for example, in red the ones that are not in the same group. So let's do this. They are not in the same group. v1 and v4 are not in the same group. v2 and v5 are not into the same group. And so v2 and v3 are not in the same group. So that's it. The fact is, like, we just this graphically, but how can we like write it with mathematics and transform it into a polynomial optimization? So there is a trick, is like for each v1, v2, v3, like for each vi, at each I, we can isolate variable xi. We say like xi equals 0 if the we associate xi if unlike if vi is into the left, so black ball in our case, then it will be xi equals 0, and if right, it will be xi is equal to 1. And so the constraints we can do to force xi to be uniquely 0 or 1 can be the polynomial equation xi squared equal xi, because minus 1 squared equal 1 and 0 squared equal 1. So that implies like xi squared minus xi equals 0. So that's it. And so if you want like to compare the ej, like if e and j are in the same group, we will see like closer to 0 or closer to 1, then we don't have our stuff like here. It will be like the case for v1 v2 or v3 v4, it's alright. But if e and j is I and j are like into two different groups, then it will be equal to 1. So e equal j, it will be 0, so we're in the same group. And so if e is different to j, then our result will be 1, and so different group. So yeah, basically we have this, and it is implied by this. Now to imply this, so from this, so this, and so yeah, I just drag the block, and so that's our main block, and so yeah, and it will give us like our stuff. Like it means like, because if they're in the same group, it just means like xi minus xj squared would be equal to 0, and here xi minus xj squared equal to 1. So yeah, so basically if we write it into the common manner, then it will just be like the set of x1 to xn of the sum of ig, believing it to e, is xi minus xg squared, such that we have xi squared is equal to xi no matter I. So it will give us 0 and 1 because it respects this constraint. So yeah, that's it. And so in the next video, we will just see that we will need matrix moments, because this problem of max cut or optimization in general is too hard to solve directly. The idea is to do some relaxation by the semi-definite programming that the computer can be able to solve. So yeah, we're gonna see this in the next video.